Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to discuss purification of colloidal solutions. Last class I have discussed preparation of colloidal solution. Now I am going to discuss purification of colloidal solutions. Colloidal solutions, when prepared, generally contain excessive amount of electrolytes and some other soluble impurities. While the presence of traces of electrolyte is essential for the stability of colloidal solution, larger quantities coagulate it. Means larger quantity is not required. Only a small quantity is required for stability of colloidal solution. It is therefore necessary to reduce the concentration of these soluble impurities to a requisite minimum. The process used for reducing the amount of impurities in a requisite minimum is known as purification of colloidal solution. Again I am telling you, the process used for reducing the amount of impurities to a requisite minimum is known as purification of colloidal solutions. The purification of colloidal solution is carried out by two methods. First, dialysis, and second method is electrodialysis. One more method is there, that is the ultrafiltration. These three methods are common. First, dialysis, second, electrodialysis, and third, ultrafiltration. Now I will tell one by one. All are easy, all are very easy. Dialysis, this concept already I have discussed. In both dialysis and electrodialysis, I had discussed same way here. That principle will be applied here. Dialysis, it is a process of removing a dissolved substance from a colloidal solution by means of diffusion through a suitable membrane. Since particles like ions or smaller molecules, particles means here ions or smaller molecules. Since particles in a true solution can pass through animal membrane also called bladder or parchment paper or cellophane sheet. Okay, all are actually this animal membrane, bladder or parchment paper or cellophane, all are used as a semi-permeable membrane. Okay, these things I told you. First I told you that animal membrane also called bladder, second parchment paper, third cellophane sheet. Okay, these are actually used as a semi-permeable membrane, but not the colloidal particles. Here, what is the role of these semi-permeable membranes? You try to understand. Since the particles in a true solution can pass through these semi-permeable membranes, but not the colloidal particles. Only true solution will pass, not the colloidal particles. The membrane can be used for dialysis. The apparatus used for the purpose is called dialyzer. The apparatus used for this purpose is called dialyzers. What is actually this dialyzer apparatus? Then it is simple. A bag of suitable membrane containing the colloidal solution is suspended in a vessel through which fresh water is continuously flowing. The molecules and ions diffuse through membrane into the outer water, and pure colloidal solution is left behind. Very simple way. Again I am telling you, a bag of suitable membrane containing the colloidal solution is suspended in a vessel through which fresh water is continuously flowing. The molecules and ions diffuse through membrane into the outer water, and pure colloidal solution is left behind, because here true solutions and ions are smaller than colloidal particles. Hence only this true solution or ions only passes, not the colloidal particles. Okay. Then this way it is a purification of colloidal is done. Purification of colloidal solution is done. Now second method, electrodialysis. Electrodialysis. Ordinarily the process of dialysis is quite slow. It can be made faster by applying an electric field. If the dissolved substance in the impure colloidal solution is only an electrolyte, means iron should be there. Suppose impurities are ions, only then it will be, this method will be applied. It can be made faster by applying an electric field if the dissolved substance in the impure colloidal solution is only an electrolyte. This is the condition. The process is then named electrodialysis. This process, when this electricity is applied, okay, when electricity is applied or EMF is applied, then this process is known as electrodialysis. The colloidal solution is placed in a bag of suitable membrane, while pure water is taken outside. Electrodes are fitted in the compartment. The ions present in the colloidal solution migrate out to the oppositely charged electrodes. This already I have discussed in details. Now third method, that is the ultrafiltration. Ultrafiltration is the process of separating the colloidal particles from the solvent and soluble solids present in the colloidal solution by specially prepared filters which are permeable to all substances except the colloidal particles. Again I am telling you, listen carefully. Ultrafiltration. Ultrafiltration is the process of separating the colloidal particles from the solvent and soluble solids present in the colloidal solution by specially prepared filters which are permeable to all substances except the colloidal particles. Means this filter will allow only this solid can be passed. It will allow only soluble solid to pass through it. Okay, and colloidal particles will be not allowed. Okay, then by this way this colloidal solution can be purified. Then a special filter paper is prepared. Okay, colloidal particles can pass through ordinary filter paper. Listen here again carefully. Colloidal particles can pass through ordinary filter paper because the pores are too large. However, the pores of filter papers can be reduced in size by impregnating with colloiding solution to stop the flow of colloidal particles. The usual collodion, actually I am telling you one term, collodion. The usual collodion is a 4% solution of nitrocellulose. Because you want to make a hole or pores small, for that purpose 4% solution of nitrocellulose is used, and that is actually called collodion. The usual collodion is a 4% solution of nitrocellulose in a mixture of alcohol and ether. This nitrate solution, 4% solution of nitrocellulose in a mixture of alcohol and ether is made. That will actually make the big hole small. An ultrafilter paper may be prepared by soaking the filter paper in a collodion solution, hardening by formaldehyde. This filter paper can be made hard by formaldehyde and then finally drying it. Thus, by using ultrafilter paper, the colloidal particles are separated from rest of the materials. Ultrafiltration is a slow process. To speed up the process, pressure or suction is applied. Here again extra condition can be applied. Ultrafiltration is a slow process. To speed up the process, pressure or suction is applied. The colloidal particles left on the ultrafilter paper are then stirred with fresh dispersion medium. Dispersion medium is solvent to get a pure colloidal solution. See how easily purification can be done by dialysis, second by electrodialysis, and third by ultrafiltration. Now I am going to discuss properties of colloidal solution. It is very simple way you are studying. Preparation, after that purification, and now properties. Correct? Every time all compounds or methods are studying like that. Particularly compound is prepared, then purified. Correct? Then what are their properties you are studying? Same way here you are studying for colloidal solution. Then now you have now you are knowing how to purify the colloidal solution. Now how will you what are the properties? Now properties I am going to discuss. Then here many properties are there. Then one by one I will discuss. Okay. Various properties exhibited by colloidal solutions are, now I am telling you. First you can say colligative properties. First property is colligative properties. Second property is Tyndall effect. Okay. Third property is Brownian motion. Okay. Then or Brownian movement. Like that way many properties are there. One by one I will tell you. Then here first I will tell about the colligative properties. Then you know already I discussed colligative properties depends upon the number of particles. Number of particles. Number is important. What type of particles are there, that is not important. How many particles are there, their number is important. Okay, just you keep in mind. Colligative properties being bigger aggregates, already you know colloidal particles being bigger aggregates means collection. The number of particles in a colloidal solution is comparatively small as compared to true solution. In true solution it is a number is more, but here in colloidal solution number is less because it is a aggregate or you can tell associated molecules like 10, 15, 20 molecules are collecting together, associating. Then that 20 are coming is called one particles or one molecule, like that. That's why there in colloidal solution number is less. Number of particles is less in comparison to the true solution. Hence, the value of colligative properties like osmotic pressure, lowering of vapor pressure, depression in freezing point, and elevation in boiling point are of a small order. Okay, are of a small order as compared to the value shown by true solution at same concentration. Concentration will be same, but numbers are in colloidal solution it is less. It is less in comparison to the true solution. True solution. What we are telling always solution. That is a true solution. Okay. That's why these properties, osmotic pressure, lowering of vapor pressure, depression in freezing point, and elevation on boiling points is of a small order as compared to values shown by true solution at same concentration. Now second property is Tyndall effect. Tyndall effect. What is actually Tyndall effect? Just to understand. It is also very easy to understand. If a homogeneous solution, same phase, if a homogeneous solution placed in dark is observed in direction of light, it appears clear, and if it is observed from direction at right angle to the direction of light beam, it appears perfectly dark. These two things you have to understand. Okay. If a homogeneous solution placed in dark is observed in direction of light, it appears clear, and if it is observed, two times you are observing. First you are observing in the direction of light, and other you are viewing that is the perpendicular. Okay, means perpendicular to the direction of light beam. Okay, then means solution you have kept in dark and you are passing the light. Then if you will see the solution in the direction of light, it appears clear. You can see very clearly. And if it is observed from the direction at right angle to the direction of light or beam, it appears perfectly dark. You can't see anything, perfectly dark. Colloidal solution viewed in the same way may also appear reasonably clear or translucent by transmitted light, but they show a mild to a strong opalescence when viewed at right angle to the passage of light. That is, the path of the beam is illuminated by a bluish light. This effect was first observed by Faraday and later studied in details by Tyndall and is termed as a Tyndall effect. In simple way, when if you can say colloidal, through the colloidal solution, if light beam is passed, then in that way, if you will see in the direction of light beam, then it will be clear. Okay, it will be clear. But if you will see perpendicular, then it will be not clear. Okay, it will be not clear. When viewed at right angles to the passage of light, the path of the beam is illuminated by a bluish light. Bluish light you will find when you will see that right angles to the passage of light. Okay, this effect is called Tyndall effect. The bright cone of the light is called Tyndall cone. Both questions are asked, what is the Tyndall effect, what is the Tyndall cone. The Tyndall effect is due to the fact that colloidal particles scatter light in all directions in a space. This scattering of light illuminates the path of beam in the colloidal dispersion. Due to light is dispersed, light is scattered to the particles, colloidal particles. Tyndall effect can be observed during the projection of a picture in the cinema hall due to a scattering of light. By dust and smoke particles present there. This Tyndall effect also can be observed. You might have seen also. Tyndall effect can be observed during the projection of picture in cinema hall due to a scattering of light by dust and smoke particles present there. Tyndall effect is observed only when the two conditions are there. First, when the diameter of the dispersed particle is not much smaller than the wavelength of light used. This is the condition. First condition, that is the diameter of the dispersed particles is not much smaller. It should not be very smaller, not much smaller than the wavelength of the light used. Second condition, that the refractive indices The refractive indices of dispersed phase and the dispersion medium differ greatly in magnitude. Both refractive indices of dispersed phase and dispersion medium differ greatly in magnitude. Then only on this condition you will see the Tyndall effect. You will observe the Tyndall effect. Tyndall effect is used in distinguishing between a colloidal and true solution. One scientist, his name was Sigmondy, Z-S-I-G-M-O-N-D-Y, Z-S-I-G-M-O-N-D-Y, Sigmondy, that is silent. Okay. In 1903, used Tyndall effect to set up an apparatus known as ultramicroscope. There they have used Tyndall effect in setting up these things, ultramicroscope. This Sigmondy in 1903 used Tyndall effect to set up an apparatus. That apparatus is known as ultramicroscope. An intense beam of light is focused on the colloidal solution contained in a glass vessel. The focus of the light is then observed with a microscope at right angles in the beam. Individual colloidal particles appear as bright stars. When they saw from microscope at a perpendicular, at right angle, then what he observed? Individual colloidal particles appear as bright stars, okay, against the dark background. You have seen that in the sky, just everywhere dark, then there a star will be there. Then like that way it was observed. Individual colloidal particles he observed as bright stars against a dark background. Ultramicroscope does not render the actual colloidal particles visible, but only observe the light scattered by them. Okay, particles, colloidal particles scatter the light. That they have seen they have not seen the particles, colloidal particles. They have seen the, you can say, light scattered by colloidal particles. This ultramicroscope does not provide any information about the size and shape of colloidal particles. Now, next properties I am talking about color. Okay, color, and after that properties change on colloidal particles, not change with this charge on colloidal particles. Okay, these after that other properties is also there, like electrophoresis. Then now again I will discuss first. Now I am telling about the color. Then I will come about the Brownian movement. Then color. The color of the colloidal particles, the color of the colloidal solution depends on the wavelength of light scattered by the dispersed particles. The color of colloidal solution depends on the wavelength of light scattered by dispersed particles. The wavelength of light further depends on the size and nature of particles. The wavelength of light further depends on the size and nature of particles. The color of colloidal solution also changes with the manner in which the observer receives the light. For example, a mixture of milk and water appears blue when viewed by the reflected light and red when viewed by the transmitted light. Okay, very conceptual things. The mixture of milk and water appears blue when viewed by the reflected, and red when viewed by the transmitted light. Means sometimes if you pass the light, then light will reflect, it will come back, and that time it will look blue, but some light will be absorbed. Then if absorbed light, when it will pass through pass through the solution, then if you will observe that light which entered the solution and passed through the other end, then that time it will appear as a red. Okay. Finest gold. Now another example I am telling you. Finest means very powdered form. Finest gold sol is red in color as the size of the particles increases. Okay. Gold particles I am talking very powdered form. Finest you can tell, very small particles of gold. Gold sol is red in color as the size of particles increases. Okay. This I told you about the gold, that it will appear as this solid red. This gold sol is red in color, but now what will happen? As the size of the particle increases, it appears purple, then blue, and finally golden. Okay, means gold solution, gold sol solution is red when it is a finest, very small particles. But if its size increases, as the size of particle increases, it appears purple, then blue, and then finally golden. Gold color, gold, it is a yellow color, correct? Then it is the big size, very big size. What we see, that is a very big size. But if very small, then then that solution, gold solution will be red when it is very fine, and as the size increases, it appears purple, then blue, and finally golden color. This I have discussed about the color. Now I am going to discuss next property, Brownian movement. Brownian. Okay. What is actually Brownian movement? Actually it is the zigzag motion. Colloidal particles, it will be not static, it will be always in movement. Up, down, left, right, everywhere it will be in a movement. That is called zigzag movement. Z-I-G, zigzag, Z-A-G, zigzag motion. It is related to that. When colloidal particles are viewed under a powerful ultramicroscope, the colloidal particles appear to be in a state of continuous zigzag motion all over the field of view. This motion was first observed by the British botanist. He was botanist. His name was Robert Brown and is known as Brownian movement. The motion is independent of the nature of the colloidal or colloids. The motion is independent of nature of colloid. whatever type of collide may be, but movement will be there, zigzag movement will be there. It does not depend upon what type of collide is there, but depends on the size of the particles. Okay, but this movement depends upon the size of the particles and viscosity of the solution. Smaller the size and lesser the viscosity, faster is the motion. If viscosity is more, means just like more viscosity means more restriction. Okay, then smaller the size and lesser the viscosity. Then if viscosity is less, faster is the motion. The Brownian movement has been explained to be due to unbalanced bombardment of particles by the molecules of dispersion medium. Why this movement is there? Zigzag motion. What is the reason for zigzag motion, Brownian movement? Then it has been explained to be due to the unbalanced bombardment of the particles. Unbalanced bombardment of the particles by the molecules of dispersion medium. Dispersion medium, particles are just attacking, always they will bombard on the colloidal particles. The Brownian movement has a stirring effect. Always it will be in a movement. The Brownian movement has a stirring effect which does not present the particles to settle. It will not allow, it will not permit. This Brownian movement has a stirring effect. Always it will be moving, which does not permit the particles to settle, and thus is responsible for the stability of salts. Due to this movement, this salt will be stable. For the stability of salt, means colloidal salt, that this movement is required. If a movement will stop, then what will happen? All particles will accumulate and will settle down. Then it will lose the property of colloidal solution. Colloidal solution means always it should be suspended. It should not settle down. Okay, just like this mud particles, mud is dissolved in water. Then you will find that always it will not be clear. All particles will not settle down. Big particles will settle down, but very small particles which is coming around under the range of these things 1 to 100 nanometer size, that is the colloidal size, then that particle will be suspended. It will not settle down. That type of solution actually is colloidal solution. Okay. Then now I have told about this Brownian movement. Next property is charge on colloidal particles. Actually all questions are asked. 1 mark question, objective type question, multiple choice question, all whatever I am discussing, all question is asked many times, not only in one examination, in different examination, in different way, form, this question has been asked. Okay, then now I am telling you about the charge. This is also very important. Charge on colloidal particles. That on colloidal particles, what type of charge will be there. Then here means many examples are there, you have to remember. Okay, colloidal particles always carry an electric charge. The nature of this charge is the same on all the particles. All particles will have same charge. If negative, then all will be negative. If positive, then all will be positive. Why same charge? Because in same charge, repulsion will be there. Then they will not settle down. Always they will be in motion, suspended. Hence, for this repulsion purpose, for this repulsion is the requirement for colloidal salt. Okay, repulsion should be there so that all particles should be in a movement, means suspended. Then this colloidal salts may be in all particles may be negative, or sometimes all particles will be positive. Okay, and colloidal particles always carry an electric charge. Okay, the nature of this charge is the same on all the particles in a given colloidal solution and may be either positive or negative. Then now I am telling few examples which has a positively charged particles. Colloidal you can say salts, some colloidal salts have only positive charge. All particles are positively charged. Then what are their examples? You remember, because question is asked. Then first example is a hydrated metallic oxide. Example Al2O3 XH2O, because it is hydrated, means water molecule is adsorbed. Then Al2O3 XH2O. And other example is CrO3 XH2O, chromium oxide, aluminum oxide, chromium oxide, and ferric oxide, Fe2O3 XH2O. All are XH2O, water is absorbed. Then aluminum oxide, chromium oxide, ferric oxide, Fe2O3. These are the examples of hydrated metallic oxide. And these oxides have positive charge. Now other example I am telling you which are positive. Then this is the basic due to this thing. I am talking about the another examples of having positive charge. That is the basic dye color. Basic dye stuffs. Its example is, in general way, basic dye stuff, but its example is methylene blue salt. This is a positively charged colloidal solution. This is the colloidal solution and its charge is positive, methylene blue. Now next example which has positive charge, that is the hemoglobin, which we are telling as a blood. Then here as example oxides, titanium oxide, TiO2, titanium oxide salt. Okay, that is actually example of positive charge colloid. Actually blood is colloidal solution. Under the inside the blood, titanium oxide is also found. Okay, then it also has a positive charge. Now few example I will tell about the negatively charged salt. Always remember, I am telling you, question will be asked. Should not confuse which is positive and negative. You should remember. Then now negatively charged colloidal salt example. First I am telling you metals, directly metals, not oxide, metals. As for example copper, silver, gold salt. means copper sol, silver sol, gold sol. This is negative. Copper sol, silver sol or gold sols. This is negative. Now another example of negative colloidal sol, metallic sulfide. Metallic sulfides. Example As2S3. This arsenic sulfide. As2S3. Arsenic sulfide. Antimony sulfide. Sv2S3. Cadmium sulfide. Salts. Means salts of As2S3. Salts of Sv2S3 and CDS. Okay, means arsenic sulfide salt, antimony sulfide salt, cadmium sulfide salts. All have negative charge. Next example is acid dye. Basic dye is a positive charge. Already told you basic oxide. But acid dye stuff, as for example, eosin, Congo red, means salts of eosin. Eosin salt you can tell, Congo red salts. All are negative charge. Okay, eosin salt, Congo red salt. Now other example I am telling you, salts of starch, gum, gelatin, clay, charcoal, etc. all have negative charge. Means starch salt, gum salt, gelatin salt, clay salt, charcoal, all are negative charge. Okay, you have to remember all these things. Now again further about the charge. The charge on the sol particle is due to one or more region from where charge is coming and for why charge is required. The charge on the sol particles is due to one or more regions. Example, due to electron capture. First one region is due to electron capture. If we accept the electron, then it will be negative. Okay, due to electron capture by sol particles during electrodispersion of metals. Due to electrodispersion of metal, that time it will capture electron. Second reason, due to preferential adsorption of ions from solution. And third, due to a formation of electrical double layer. These three reasons are there. First I told you, due to the electrodispersion of metal, that time it will absorb the electron, capture the electron. Second, due to preferential adsorption of ions from solution, because in solution may be negative charge or positive charge. Then by giving some preference either for negative charge or positive charge, for any charge it can give preference due to that. And third, I told you, due to formation of electrical double layer. Now suppose one layer of negative was there, then now this negative charge may attract positive charge as a second layer. One layer of negative charge, then other layer will be of positive charge. Then this is called electrical double layer. And only here I want to tell you that two layers are there, negative and positive. Electrical double layer. Then due to this electrical double layer, it can create potential. It can create potential due to the electrical double layer. Wherever two charge will be there, two charge will be there, and negative and positive very close to each other, then there it will produce potential, don't forget. Then this I have told you. Further I want to tell you, preferential adsorption of ions is the most accepted region. This preferential adsorption of ions is the most accepted regions. The salt particles acquire positive or negative charge by preferential adsorption of positive or negative ions. When two or more ions are present in the dispersion medium, preferential adsorption of the ion common to the colloidal particles usually take place. Okay. In solution both are present, negative and positive. Then any one it can absorb. This can be explained by taking the two example. Okay. I will tell you that first I am telling very interesting. Two examples I will tell you. Then first example I am telling you, when silver nitrate AgNO3, when silver nitrate solution is added to a Ki solution, potassium iodide solution, the precipitate silver iodide, you know that silver nitrate AgNO3 plus Ki, it will form silver iodide. It will form silver iodide, you know. Okay, that is means you will get precipitate of silver iodide Agi. Then when silver nitrate solution is added to a potassium iodide solution, the precipitated silver iodide, this precipitate I am talking about silver iodide, absorbs iodide ions. It absorbs iodide. Silver iodide absorbs iodide ions from the dispersion medium, and because it absorbs I minus, it absorbs silver Agi absorbs I minus from the solution, that it is negative charge. It became negative charge. Okay. And negative charge colloidal solution results because it absorbed I minus. However, when Ki, now you are adding Ki solution. When Ki solution is added to silver nitrate, opposite way. In the beginning, you have added silver nitrate in Ki, then it got negative charge, iodide ion it absorbed. But in reverse way, Ki you are adding in silver nitrate. Means Ki is now dispersed phase. Ki is dispersed phase. What you are adding, that is the dispersed phase. Then now when Ki you are adding to silver nitrate solution, in that situation, when Ki solution is added to AgNO3 solution, positively charged salt results due to adsorption of Ag plus. Now Ki will absorb Ag plus ions from dispersion medium. Correct? This is very, very interesting. Now second example I am telling you, that is of FeCl3, ferric chloride. If FeCl, this way only you have to understand. If FeCl3 is added to excess of hot water, now FeCl3 you are adding to hot water, excess hot water, means hot water is a medium, dispersion medium. FeCl3 is dispersed phase. Then what will happen? A positively charged salt of hydrated ferric oxide is formed due to adsorption of Fe3 plus ions. Means water has now in this case adsorbed Fe3 plus ions. That's why it becomes positive. However, when ferric chloride is added in NOH solution, now actually first FeCl3 ferric chloride is added in the hot water, then hot water absorbed hot water, in presence of hot water is converted to ferric oxide, and ferric oxide absorbed Fe3 plus. Okay, FeCl3 is added to excess of hot water. A positively charged sol of hydrated ferric oxide is formed due to adsorption of Fe3 plus ions. However, when ferric chloride is added to NOH, then what will happen? A negatively charged sol is obtained. Negatively charged sol is obtained, okay, with adsorption of OH ions. In both cases, actually after the reaction, they will form a ferric oxide, and that ferric oxide, in the first case, they have absorbed these things, Fe2O3, hydrated Fe2O3 in the first case absorb iron, Fe3 plus. That's why it becomes positively charged. And in the second case, FeCl3 plus NOH, again it forms ferric oxide only, Fe2O3, hydrated Fe2O3 plus, now it adsorbed OH minus. That's why it became negatively, okay, negatively charged. Then this I have told you how charged is formed, negative or positive. Having acquired a positive or a negative charge by selective adsorption on the surface of a colloidal particles, this layer attracts counter ions. This layer attracts counter ions from the medium, forming a second layer, means electrical double layer I am talking about. Now suppose negative this colloidal was there, AgI absorbed, suppose iodide ion, silver iodide absorbed negative ion, means I. Then this negative colloidal particles means AgI, and it absorbed I minus, that is the negative. Then now this negative, it will attract counter ions, means opposite, because in the solution potassium was there, K plus was there, because silver nitrate plus KI added, then K was in the solution, then this negative colloidal particles will attract positive potassium, and it will form double layer, that is called electrical double layer. Likewise, again silver iodide, suppose it attracts Ag plus, you have seen silver iodide attracted Ag plus, then now colloidal particle is positively, then will attract negative. Then negative is means what? In solution iodide was there in solution, then this positive colloid will attract negative iodide ion, and it will form electrical double layer. Okay, the combination of the two layers of oppositely charged around the colloidal particle is called Helmholtz electrical double layer. This question is asked, very important. This electrical double layer is called Helmholtz electrical double layer, HELMHOLTZ. It is the name of scientist, Helmholtz electrical double layer. According to modern view, the first layer of ion is firmly held, means strong. First layer of ion is a firmly held, means strong, and is a termed fixed layer. This is called fixed layer because it is strong, while the second layer is mobile, means moving, not strong. Second layer is mobile, which is termed as diffused layer. Then one is fixed layer. First layer is fixed layer, second layer is diffused layer. It may diffuse in the solution. That's why it is called diffused layer. Since separation of charge is a seat of potential, since separation of charge is a seat of potential, the charges of opposite sign on the fixed and diffused parts of the double layer results in a difference in potential difference. It produces potential difference or potential. This produces difference in potential between these layers. This potential difference between the fixed layer and the diffused layer of opposite charges is called electrokinetic potential. It's called electrokinetic potential and also called zeta potential. ZETA, zeta potential. It is most important electrokinetic potential or zeta potential. Okay, this is very, very important. The presence of equal and similar charges on colloidal particle is largely responsible in providing stability in the colloidal solution. Already reasoning I told you, same charge repulsion, hence all will not come together, means they will not settle down, means they will not precipitate. Okay, this is the plus point of having the same charge, because the repulsive forces between the charged particles having same charge prevent them from I can say coalescing, COLESCING, coalescing or aggregating when they come closer to one another. Okay, this I have told you about the some properties. Now other properties are also there. Today it will be late, that's why I am stopping only here. Next class remaining properties I will discuss. Thank you.